Hello, I'm Alexander Bystrov, and today we are talking about the Internet. It's a part of our module on machine-to-machine technology IoT, and the Internet sits underneath this technology, so the technology builds upon that, so we need to start with the background. Our aim today is to have the necessary background on the Internet so we could later construct a machine-to-machine network by using this kind of connectivity technology. Our objectives are to remember the OSI reference model and skip in it the level number 1, which is good, so I'm going to talk about this. This is the physical layer, and computer scientists usually do not like it. Right? So it's the business of communications engineers to deliver signals from one point to the other. Then goes the OSI level 2, which is the link level. It is already a logical level, and in the logical level we are dealing with packets and formats, and we are not concerned with voltages or modulation of signals, radio signals. So this is what we are going to start with, and we'll see a couple of examples of MAC. Right, it's media access control, so it's the level otherwise known as MAC. There are MAC addresses there. It's the level at which wires or air, right, radio waves, send the most basic packets around frames. Then we'll go at the next level, which is the network level. And the network level, it is where packets can travel away from our laboratory and into a different country, in fact. Right. We will see basically that the second level of the OSI, it's specifically designed for communicating on a very defined small network, otherwise known as LAN, local area network. And level 3, it is for interoperation of those LANs. And you have one LAN there, then many LANs next to each other, and a packet can be sent from this LAN across many other LANs to some remote LAN far away from us. So that's the purpose of that. And then we will talk about the OSI level 4. It's where messages are cut and split into small fragments, which are packets, and sent separately, and then on the far end they are assembled back. And as they are getting assembled back, then we get the message back, right? So if one of those fragments are lost, then it's also the business of this layer to make sure that it is recovered somehow. How it can be recovered? Through a request to retransmit another copy, for example. So several levels will be covered. So we are starting with level 2. This is our OSI reference model. And now I'm repeating what I just said, so we are going to skip this level, which is good, is the physical level, and we will focus at these 3 levels. At these 3 levels, the data link level, it's where we are starting with, and this is where we have the Ethernet networks, right? And this is for local communication within the laboratory. And then we will add another layer. This one, it is for interoperation between the laboratories or LANs, right? And then through multiple LANs, eventually the packet will travel long distances. But different means, different packets, different fragments, different technologies. Historically, this one started first, but remarkably it is still used. Why? Because it is just included into the protocol stack. You cannot remove it. If you remove it, then this one will become suspended. It will never communicate between the actual devices. Right, on the left here we see words which are replacing basically the same thing. So frames, buckets and segments, essentially there are buckets. So when you're looking at when you're looking at a data format for each of those protocols, you will have a header and a payload, and altogether it is something, some sequence of zeros and ones, and is of particular length. It cannot be infinitely long. So essentially it is a packet, but they use different words to denote them. So at the data link they are frames, at the network they are packets, and for the transport layer they call them segments, segments of a message cut into segments and sent and reassembled. I'm not going to stick very closely to these jargon words. So essentially they're all packets, but it's good to remember. We are also not going to look at the upper levels, because this is the subject for the next lecture, where we are going to add secure shell and start a session and present the data and connect to the application. It's all this top level, not now. It is important, it's a part of the course, but not now. Now we are starting with the lowest level, which is the link layer. Link of the level number 2, and it is supported by the standards, IEEE standards, which start with the number 802. Right, there are many of them, 60 of them, right? I'm saying about because they keep adding and modifying them. But there are plenty of those. Please have a look. They are openly published. It's quite interesting. However, I suggest to start with the overview which I'm giving you, and then proceed at your own pace. Historically, it all started with Ethernet 2, which operated over a thick cable, and it was a coaxial cable. So it has a shield like a pipe, and there is a wire going through, and it's shielded first of all, so it's immune to interference, and is a radio cable, so it's capable to propagate very high frequencies. So they use this high frequency cable because the original intention was to run this cable at a very high speed. What is the high speed? We started with 10 megabit per second, which is not a very high speed by the modern standards. But if you think about this, in order to transmit a pulse, which is just a square waveform, then you need the frequency range of about 3 times of the fundamental frequency of this discrete signal. Why? Because you need to propagate some odd harmonics of that, so at least an additional harmonic on top of the fundamental one, so at least 3 times the frequency. Probably better to have it 5 times, and then instead of 50 megahertz, instead of 10 megahertz, you need the bandwidth of 50 megahertz, and it's proper radio signal. Radio signals in general begin with 100 kilohertz, it's long waves. Middle waves begin with 1 megahertz. So we are talking about shortwave range. So at the time it was very advanced technology, of course. And about the times we're talking about 80s, right? So the prototype for this was created in the 70s, but it was quite long ago, the time before the mobile phones. So another standard which succeeded the previous one, as you see, the previous one was 82, this one is 83, so they're closely spaced. It is essentially the same good old DIX, just written differently and registered with IEEE Institute of Electronic Engineers and became the standard 802.3, and it was called 10 base 5 10 megabit per second speed. So it's still the same thick coaxial cable. Right. Why is it thick? Because the size of the cable corresponds to its impedance, and in order to achieve the impedances which were selected for that, you need to have a kind of physically quite thick cable. They used, if I'm not mistaken, 50 ohm or something like this impedance. And after that, a rapid progression happened, and the speeds were increased from 10. They arrived to 100 and to 1000, and this is already a gigabit, so 1 gigabit per second transmitted. And then they keep increasing that, so 5 gigabit cables exist and so on. If you wish, you can look at the standards, but the significant difference happened here when going from just the basic 82.3 to 82.3U, because here you have this coaxial cable which connects all computers, and they all connect to the cable in parallel. And here we have a computer, and a switch between them, so they're connected with an individual cable to that switch device, and there is no parallel connection to the single cable. So they moved some complexity of the physical layer implementation into a separate device, and they achieved higher speeds as a result. And also they managed to, probably by adding complexity to that central device, probably because of that, they managed to simplify the implementation of the cable itself. So instead of a very expensive thick coaxial cable, now they're using Cat 5, Cat 6, these days there are Cat 7 cables, right? So what are they? So they're twisted pairs cables, so the information is carried through two wires without kind of coaxial shield around this, and these wires are just twisted, and the energy of the wave sits in between all those wires, the high frequency energy. Well, in Cat 6 and 7 cable, 7 is not included here, they actually also have this shielding around it as well, because they want to minimize interference, especially when cables are closely spaced. You may need this, and also for security, for example, health reasons, you may want to encapsulate high frequency radiation into a shield. But it's not fundamental for the transmission of the high frequency energy, because it all sits in between those twisted thin wires. These thin wires are inherited from telephone cables. They switched to a well-known and very cheap technology, and it was a massive commercial driver. Still we are using it. Nowadays there is a trend to switch to something else like optical communication, but it's used at the moment between the houses, so between you can see this cable on the street, but inside the home probably you will have something made with copper, and will be Cat cables, most likely Cat 6 these days, most popular Cat 7. Cat 6 is needed for 1 gigabit internet, and Cat 7 usually it's not needed. Those Cat cables, they're mostly compatible between themselves, by the way, starting with 5E, in the sense that they will work if you take this Cat5e, it will work on a gigabit internet. However, the quality of the cable may be not enough to have a very long link. So they have the same connectivity, but the quality of cable can be slightly different. This Cat5 and Cat5e, they are significantly different cables. So here you have fewer wires inside. So in Cat5e they use several channels which work in parallel. It's one of those tricks by which they manage to increase significantly tenfold. You see, they increase tenfold the throughput of the cable. Right, the link layer may or may not include additional layers. These are PPP with the version OE, or PPP without OE. This is point-to-point protocol. Point-to-point over Ethernet or just point-to-point protocol. It's an old protocol which comes from good old connection between just fixed two devices, and we are just streaming the data between the two. It was widely used when computers talked over the telephone, so you dial the other end of the line and then you have the connection established, and once the connection is established you don't really need to have any addresses after that. You're just sending the data along. All you need is just to have the identifier for the stream, because first you are sending one file, then another file, so you need to have this identifier. So it's a simplified protocol. Over the Ethernet PPP, it's a wrapper around this one, where we have the destination Ethernet address added, and you will see very soon what this Ethernet address means. So Ethernet was invented in 1973, they say so, although it was not Ethernet, Internet just yet, it was Ethernet. It was invented within a Xerox company by a brilliant engineer, Robert Metcalfe. So this is his drawing, and it's worth looking at. This is whitish line. This is the cable. He called it the ether for some reason, right? It's coaxial cable, radio frequency cable, and has, you see those bars at the ends, which are so-called terminators. The terminators are needed for transmission lines because they have some sort of characteristic. It is an impedance of the cable, right? It's due to the inductance and capacitance of different components of that. And the value of this parameter is such that if you put a resistor at the end of the cable whose value matches the impedance of the cable, then any wave arriving from the cable to the end of the cable, to this resistor, will just heat up the resistor and nothing will be reflected back. If you remove the resistor, then the wave comes and just reflects and goes back, and the reflected wave in one cable creates interference. If you short circuit the far end of the cable, the wave also comes and reflects back, so it reflects from both low or high resistance ends, and if you have a matched resistance there, a terminator, then reflections don't happen. So they have those terminators here, which means that if you inject any wave, electromagnetic wave in this cable, it will, for example from here, it will travel one way and the other way, and will reach the ends and will disappear there. So there will be no reflection and kind of multiple cycles of traveling it there and back. It's just a electrical trick which they did, so it's not important probably for the understanding of protocols. Now, this is one device, this is another device, third, fourth. Right, so each device looks like this. The device is your computer basically with a network interface card. So it has a physical transceiver whose business is to apply voltage to the inner wire inside the cable. It's coaxial, so outside is a shield and inside there is a thin wire going through. So it applies that voltage to the wire and sends the wave. So it's transceiver. There are some switches there, transistors there. There is a kind of interface connection to this block, and this block has the interface. The business of the interface is actually to convert whatever the data comes from the controller, that's controller C, into a sequence of bits, and the bits are sent by means of the electrical circuit here, and the business of the controller is to take the data stream from here and form those combinations of zeros and ones which are given through a bus to the interface. And this unmarked part on the right, it's your computer basically, it's your processor, whatever it is. It doesn't need to be a processor, but whatever it is a processor. And there are many such devices on the same cable, and if you want to communicate data between this device and, for example, this device, then you send something and this packet is recognized by this guy and accepted, right? But the trouble is that when you are sending the data from this to this, at the same time this one may try to talk to somebody else on the same cable, and then physically the voltages and currents and waves will interfere and obscure each other, destroy each other. So what happens next? Well, apparently such a system has, in the transceiver circuitry, it has a special device for detection of such collisions. So if you are trying to drive the wire to the logic 1, at the same time it's driven by some other part to the logic 0, then increases the current because of the conflict, and this increased current is sensed and the signal goes into the controller, says just don't do it, just wait. It is a so-called collision detection system. And there is also another system here which is collision avoidance or exponential back-off algorithm. So what they did, once a collision was detected, then both controllers, this one and another controller in different machine, registered that and just went quiet for a moment, and this period of being quiet, the quiescent period, was selected at random, and the next time they try to talk to each other, then usually the collision didn't happen. But as we have many devices on the same cable, then it's also possible that the second time you try to talk and another collision happens within a different pair of devices. Then what happens? It's an exponential back-off, so the device again goes into the quiescent mode. It sits quietly, but this time it sits quietly for longer. So if you have many collisions, then more and more devices go into this waiting mode, and thus they will reduce the utilization of the cable, and there will be gaps, and at least some traffic will be allowed there, so it will be not a constant collision going on. Well, speaking of constant collisions, I played and used such networks, and they are not very robust in the sense that if you have this cable which is very long, and somewhere in the cable you have a short circuit, or one of your network interface cards is malfunctioning, short circuits the cable, then the entire cable just dies. Nobody else can talk on it. So the system relies on the operation and correct operation of all network interface cards connected to it. Well, these days they replace the cable with special device, and now we don't have this problem. So this multiplexing and demultiplexing is not done through the parallel connection to the same media, but instead of that the media is virtual. virtual in the sense that it's represented by a device which pretends to be a cable, but it's not. I mentioned here Aloha protocol. Aloha, it's a wireless protocol. They actually implemented this earlier than Robert Metcalfe, his Ethernet, and the idea of that was also to transmit packets but wirelessly. Aloha is historically important, but it's not a direct basis for the current networks. Now this is the format of that frame or packet which is sent by the network interface card, and this is important because it's still the same it was as before. And let's look at the fields. You will actually see those when experimenting with the network. So it has an important part here, that's the payload. This is the data which we are sending across, right, from one device to the other. It's the payload which is being sent. Right. Apart from the payload, we have this thing which is a header. It's called MAC, or Media Access Control header. The purpose of this header is to do addressing, so it contains the destination where the packet is traveling to. It also contains the source address. Why? Because you send the packet there and you expect the other party to respond to you somehow. Of course you can include this information into your payload somewhere, but why? Because the whole protocol is designed to do this kind of bidirectional communication, establish a connection, carry on this kind of bidirectional communication. So this is the indicator of the return path. And this is the field which is really optional. Its purpose is to see here different values, this, to indicate of what kind of packet we are sending. Why is it included into this field, into the header? Because headers are processed in hardware very quickly, and the payload is passed into the processor, and processor does something with this. So to assist fast networking, they decide to include here some indicators of purpose of the packet, and then it will hopefully help to deal further with this packet somehow. In particular, we can distinguish between types of the Internet protocol which sits inside this payload, whatever it means sits, because we are yet to cover Internet protocol. It can be an ARP packet. ARP is actually quite an important packet in the sense that when you connect your computers to the same LAN and they start talking by means of the Ethernet, they need to introduce themselves to each other. So they need to know the MAC addresses of each other. So this ARP means Address Resolution Protocol. So within this protocol, the computers tell each other which MAC addresses they have. And also actually they communicate information about the IP addresses, but we are not covering it just yet. And then within the LAN they can talk to each other, calling each other by first name rather than somehow else, and know each other. Well, once the standards were introduced at the early Ethernet 2 and eventually Ethernet 82.3, then they started playing with this type field, this Ethernet type field, and according to the standard, IEEE standard, now it can be substituted with frame length. Why is it the case? Because the payload can be of different size. Yeah, it can be short or long. Right, short it's 46 bytes, and data can be up to 1500 bytes. Kind of a lot of data. And as the size of the payload can be different, so you need to know when to stop receiving it. This information about when to stop receiving it can be communicated through the physical layer, of course, but in many cases this can be convenient to also know in advance when the transmission begins, to know when you're going to finish. Right. In general, the earlier information appears in the packet, or in the header of the packet actually. The header is the first, so earlier the header appears, faster it gets into any hardware which processes the packet, and then it is possible to make decisions or any actions earlier, before you have received the tail of the packet. So you're still receiving in the process of receiving a packet, and then during this process you can already start doing useful things. Otherwise you will have to receive the entire packet, record it, store it in a register, then analyze and make those decisions, which is a slow process. Right? So faster is to keep doing things while receiving it. Please have a look at the standard, which is at the IEEE website here. Right. It is a standard, it's a large document. I don't think it makes sense to learn it by heart, but it makes sense to know where it is and what it looks like. Ethernet MTU. So the keyword here is MTU. What is that? It is a maximum transmission unit. Right. So you know that the size of the packet can be different. It can be short, can be long. And why is it? What limits the size, and how did they select the maximum length of that thing? Apparently, the payload for the Ethernet is designed to carry either packets for the internet IP. Yes, that will be the packet for the, like yesterday, consider those H2 headers, right? So the address somewhere, not here, but in Spain, sending it far away from here. Or it can be a different story. It can be those PPP protocols, point-to-point protocols, and slash separated are PPP and PPP over the Ethernet, PPPoE. So what are they? Point-to-point protocols are designed to transmit the data between, once the connection has been established, as usually telephone line or something like this. So I don't need to address much, and this is an example of this. PPP, for example, is transmitting this data, right? And the red is the PPP protocol. So it adds to the data that small part in front, which is 2 bytes of the PPP identifier. So if you don't have addresses there, then you need to distinguish between the first and the second file, one session and the other session, so you need to have this identifier. Not much overhead, but red is a different packet from the purple one. Alright. Then the yellow is another addition to this red, and this addition is 6 bytes of something else. Right? What is added here, it's the MAC address, because designed to communicate over the Ethernet. So basically PPP over the Ethernet also carries information in which direction to send this packet. So, and the packet can be a part of a longer sequence. So all those which are sent with this ID in the exact sequence as they have arrived to the destination, then they will be assembled together into a file, and it is assumed that the connection is reliable because it is similar to some RS-232 serial interface or something like this. So you establish the connection, and any collisions are not possible there. Well, faults of course are possible, but sort of, the system is not supposed to operate under faults. Now we have this yellow packet, and this yellow packet is quite large, and apparently it can occupy up to to what? Up to some significant number, right? This one. And it's for 1492. It is specified in the standard, and this document is available on the internet, the standard of the end of the last century. Now this payload is encapsulated into the frame of the Ethernet, and the Ethernet frame adds the header. Right. So that's how it works. They for some reason decided to change this number into 1500 at some point. I'm puzzled why they did it, because the numbers are very close to each other, and this change does not result in any significant or noticeable at all increase in performance. So it looks like that at the beginning the engineers were very tight with those numbers, because everything was implemented in hardware, and the buffers were fixed, and it was quite strict about this. And at some point later everything became programmable, and memory chips became quite cheap, so you don't need to synthesize every time the memory. Just take a chip which is excessive in terms of memory anyway, so at some point they just rounded it up and started producing the equipment. And once the equipment became so popular that it was tolerant to violations of the standard, and all equipment around like that, so they decided not to fiddle with strange numbers and just round it up to 1500. It's not important, but important is to memorize this number. And also it is important to know that if at any point you are facing a problem that some network refuses to propagate or accept your packets, then it can be the reason that they're still using the quite old standard. Right. Well, you will not find this frequently. Why? Because hardware these days is plug and play. The devices negotiate the common protocol and the sizes. Now, this is the Wi-Fi packet. It is in a way similar and in a way different from the Ethernet packet, although it is also a media packet, so it goes through the media. Just media is not cable but air and waves, electromagnetic waves there. It is also the same link layer of the OSI reference model. It also contains MAC addresses. MAC addresses are of the same size. Used to be 6, and now it is still 6 bytes there. However, there are differences. There are some new fields added, and you see there are many more addresses here. So instead of 2 addresses which are source and destination, now you have source, destination, and 2 intermediate addresses which serve an interesting purpose. The frame body, here you have the data encapsulated. The data encapsulated can be of a size which is different from the Ethernet packet. So you have the wireless card, the data arrives into this through the Ethernet. Payload is 1500, and here it will be different, and the numbers are here. Why is it different? I selected 2304. It became standard at some point. Wi-Fi is encrypted anyway, right? So you have wide equal privacy, so this packet inside, it arrives as clear text into the device, and then it becomes eventually this Wi-Fi packet. So the data from the original packet, from which is MTU 1500, right? It has to be encrypted somehow, and the process of encryption, its size changes. So there is no way to match one to the other, so this number is different. And actually this number is larger. Why? Because larger packets provide slightly higher throughput at the expense of latency. Wi-Fi networks are not very good in terms of their response. So, they can be high throughput, so can digest and pass through plenty of data in a unit of time. But they're not very quick, because they switch between a variety of devices in a time division multiplexing mode. So they're just switching between them and again. So if you are sending something and then receiving the response, this kind of multiplexing time will be added to the cycle of request acknowledgement. So latency is not good, throughput can be quite high. Now the fields here: FCDI, frame control, duration, connection ID. So this is specifics of how to deal with the frame, and DI it is for the connection. So you establish a connection and it is tracked at the link level. Addresses, they depend on the context, and there will be an illustration showing why we need this. Apparently with Wi-Fi you can set one access point and the other access point, and then you have your mobile phone or any mobile device, and you walk from one access point to the other, and you can bridge them together. So they will appear for all kind of practical purposes to you as a single access point. So the whole universe is covered by a single access point, and they're bridged together. And this is done at a link level. So when you're moving from the one to the other, handoff happens. When handoff happens, it means that the protocol somehow need to keep the track of the original connection, but as it moves to a different access point, it actually uses a different address, a different MAC address, and for the sending and receiving as well. So sending and receiving means that you need source and destination. So it adds to the more address fields which potentially may be required here. So the packet is more complex. Yeah. So these are my calculations of the frame body. So that's the frame, it's the length of that frame. By the way, the previous diagram for Ethernet and this one shows this field CRC. It's cyclic redundancy check. What it does, it basically quickly goes, if you apply this cyclic redundancy check algorithm to a bit string, then you produce a number, right? And this number is like a checksum for the whole thing. They call it signature. Its property is such that if you change at least one bit or several bits, then it will change. It's very unlikely that by changing several bits you will arrive to the value of CRC which is still correct. So it's difficult for one error to compensate for another error in the CRC, so it's for checking. If you wish, we can discuss how CRC works, but this is just mathematics and lookup. It's a very well known concept which is frequently used in data communication. So these are my compute values to the size of the frame under different modes of operation. This is wired equivalent privacy, this is WPA and WPA2. There are different ways of encrypting the data inside, and when they do this encryption, they also with encryption is based on keys, secret keys, and so when they do this WPA or WPA2, they do rotation of keys. They keep changing them quite quickly, because the original attempt to encrypt things was via the equivalent privacy method. It was not strong enough. Basically, they used an encryption algorithm which was not strong enough, and the key length was quite short, and it was broken. It was a failure to implement kind of a standard Nowadays nobody is using WEP as a result, and we are all on these two other things which are at the moment unbreakable by simple and common means. What I mean by this is that if you configure it properly, then probably it will be unbreakable unless Google or a government try to do that for you. Right. The details on the formats and protocols for Wi-Fi can be found here. Why? Because it is 802.11 family of standards. The previous one was 802.3. So 802 is our link level standards. The common features of link layer. It can be wireless, can be wired, can be old style cable, new style cable, so it doesn't really matter. The common features are that they're using MAC addresses. MAC addresses belong to a very small area, and they call it LAN, local area network. Local area network is different from World Wide Web, WWW, right? Different in the sense that you have full control of that, and you have knowledge of all computers there, and if you are sending something on your LAN, then this computer can address directly the low-level address of the other computer, and these addresses are MAC addresses, and MAC addresses have 6 bytes in them. It is different from what we are going to do next, and it will be the IP protocol and connecting from here to a remote country, and that the next level will be based on multiple LANs sitting next to each other, and one LAN passes the packet into the other LAN, and so on, so on, so on, so on, and each LAN has no knowledge about the internals of the next LAN, so it will be using a different address. It will be a 4-byte address, so it will be different address. So we are using different addresses. So MAC addresses is a feature of the link layer. MAC address format, it's 6 bytes, it gives us a lot of combinations, right? A lot of combinations. In the past, an attempt was to produce network devices which had all different MAC addresses, but then it was quite difficult to negotiate this between different manufacturers, and also many users wanted to create clones of computers or internet cards. Why they needed this? Because the old equipment goes offline and you want to replace it with something, and you want it to pretend to be the old one, otherwise reconfiguration is required. And so as demand existed, so they created reconfigurable MAC addresses in network interface cards, and as a result of this idea of the global control over MAC addresses was abolished completely. They still have randomly generated MAC addresses when you buy a network interface card, but there is no guarantee that there will be no repetition. And then there is no reason to worry about this, because if you have your network interface card with one MAC address which is installed here in this LAN, and the other card with the same MAC address somewhere in a different LAN, as these LANs are disconnected, so they cannot communicate at the link level, then there is no conflict. It's important not to have the same MAC address within a single LAN, so this has to be checked every time, otherwise there will be a problem. Well, you want to send a packet to this device, but the other device has the same MAC address, so both of them will receive it. Not good. So that's what I said. MAC address of the device is usually assigned at the factory, but can be changed. The data sits in the payload, and it can be either directly included or indirectly encapsulated into this point-to-point protocol, in which case Ethernet combined with point-to-point over the Ethernet and just point-to-point protocol, which is a part of that. So this complex combination is considered to be still a link layer protocol data unit. Sounds confusing, right? For us it is not confusing because we are not going to use these. Right, so those who are using point-to-point protocol, for them it is confusing. For us, our link layer will be carrying a datagram or a packet between two IP hosts for the internet implementation. So we are interested in this. So this is our bread and butter. So we'll be considering the IP packet sitting as a payload inside the Ethernet packet. So forget about this and welcome this. Various devices on the link allow transition between different instances of media. Right, so if you remember, my previous lecture was an illustration from a classical book where we had two LANs, and within one LAN we have Ethernet connections, and somewhere in the middle of that Internet connection network there was a device whose name was a bridge. Could be switch as well, but bridge, right? So what bridge does, it disconnects physically the media, but the link level addresses are the same. It's the same kind of visibility is the same, right? So you can go from one end of this bridge to the other end and access and see and access the MAC address at the far end of that. Although physically the wires are disconnected, they're put through some amplifiers perhaps or something like this, switches in between. So it is possible to have various devices within the link where you have different physical media but the same link space. Right. So these devices do not include routers, and the routers, it's the higher level, it's Internet Protocol level, and this is what we are going to talk next. Right, so we are finished with the link layer. The next is the example, and then will be the IP protocol. Now what we see here is the old style network, perhaps 10 megabit per second, because I see here a common cable. This is a coaxial cable. Those bars, these are terminators, and the computers are plugged in into the cuts in this cable, or taps, they call it taps. And this computer can talk to this or to this, and these two can talk, these two can talk, and they can start talking simultaneously, cause a collision, and the collision is resolved somehow. So it is one illustration, and modern networks look like this. So instead of a common cable which does the multiplexing, demultiplexing, whatever, everything goes through the same media, here we have some sort of device with buffers inside. So this device sends the data packet and stored here in a register, this one, and those packets, they have their destination, and this device decides when to start sending it to the destination. So when the connection is free, it starts sending it there. By performing buffering inside, it avoids collision. So here in this picture, above, if collision happens, then you have to start doing the business from the beginning. Here the collision just doesn't happen because this guy in the middle just accumulates whatever comes and then sends it to the destination whenever the link is free. So this is what we are using. We are using so-called switch. Our cables are RJ45 cables, we call them RJ45, and they have a specific connectors at the ends, and you all have seen those there in your laptops. We'll be using cables category 6, Cat6 cables everywhere. Please look up on the web what it means Cat6, how many twisted pairs they have inside. Currently they have 4 twisted pairs inside, and also shielded just to reduce interference. Very high quality cables. Examples continue with a wireless situation, wireless network. Why I decided to show it here? Because the previous one, it's one variation of the standard. It's 802.3 and this is 802.11. And the idea was here to show a picture which explains why we need multiple MAC addresses when dealing with the protocol for the media of Wi-Fi. This is our tablet with Wi-Fi interface, and these are 2 access points. They have different MAC addresses and they are bridged together through the link layer, special device MAC bridge. And when you are moving this device smoothly between these areas, it will lose connection to this one, gain connection to that one, and the protocols are built around this in such a clever way that the connection goes uninterrupted. So if you try to do this with different internet connections, it will be like unplugging it from one socket, plugging it to the other socket, so it will interrupt the transmission of a file. Here it is happening seamlessly, quite nicely. And as a result, when you are moved from here to here, you need to still keep the track of where you are connected to first, and then establish connection to a new access point and carry on. This is why they need several fields for MAC addresses. Ignore for now this part. It's the output of the whole system. It's the router which leads us to the LAN or World Wide Web. Our link level finishes at this entry. It includes 2 access points, and these access points are connected to this tablet dynamically, so it can be switched between the 2 as it moves. If you want to play with this, and I strongly encourage, it's part of our program of study, you may want to use tools in our coursework, and the tools are just programs. In each Raspberry Pi we have Linux installed, and there are standard Linux tools there. One tool is a program TCP-dump. When started with these strange options, the options point basically at this Ethernet interface. It will start capturing whatever traffic comes from that interface and printing it on the screen, and you will see the packets arriving. So you don't see the packets themselves, but you see the LED flashing. It means that on the interface, it means that the packets are arriving, and on the screen you will see a stream of zeros and ones in some strange format, which is difficult to recognize because everything is running on the screen and disappearing somewhere. If your device has a different name from that, you can check it. So if it is not your Raspberry Pi in the lab, but of your laptop at home, then you can type a command ifconfig. It's another program which fetches from the kernel of the system the information about the networks and devices and how they're configured. And from here you will find out what network device your particular computer is using, and then if you can replace this with whatever you get from there. For example, in my computer at home, I have ENO1 network. Why it's called like this? Why not just one of those names which somebody invented? Now, this stream, which is kind of moving on the screen quite fast, and you cannot make sense of that. You can save it into a file for further investigation. How we do it? The same command, right? It produces the output on the screen, which is the standard output. And you can redirect the standard output by means of shell from which you start commands into a file, dump. It will be a text file. You run this for a while, then press Ctrl+C to kill the TCP dump process, and then the file will be closed and will store the whatever data was received, and then you can analyze it and put in a report. Sounds quite interesting. If, however, you want to be quick and analyze everything on the spot, and you're hunting for a packet arriving from some interface or going to some other interface, then you can do this clever thing. The same command, right? So it produces plenty of output. Most of that is irrelevant. Its standard output is pipelined into the input of the next command, which is not a process, another program which is run. So this process, which is an instance of an executed program, it's grep. If you read the manual for this, its business is to hunt in the data stream for some particular patterns which are specified here. Just put here several digits of the MAC address in hexadecimal notation of either source or destination of any of your devices on the net, and then this grep will filter it out, and you will see by far fewer lines on the screen, only those which are specific to a particular communication. So it will be well. Right, so we have finished with the link layer. The next is the network layer. So I'm moving from what? OSI level 1 to the OSI level 2 levels in the reference one. But first, a break.